In this lesson, we will talk about the origins of the various capacitances associated with MOS devices. A MOS transistor can be thought of as a four-terminal device consisting of the gate, the source, the drain, and the body. And every pairwise combination of these terminals possesses a capacitance. The largest capacitance, the most obvious capacitance, is the capacitance arising from the gate to the bulk. Okay, and in its most fundamental form, we can think about the capacitance as the a pool of two pools of charges which are closely spaced together, whether they are separated by a dielectric or free space. And here, the free carriers, there does not need to be a metal plate. The free carriers in the gate side, free carriers in the polysilicon, or in older processes, free carriers in the metal, and the capacitance arise from the close proximity of the free carriers here, separated by the oxide here, and the free carriers in the bulk P semiconductor here. Now, transistors are also today have very small dimensions. The length of this channel is on the order of 10 nanometers. So this close proximity also gives rise to capacitance between free carriers in the source end region and the gate, and free carriers in the drain end region and the gate. So there are capacitances here also contributing, and together the gate to source, the gate to bulk, and the gate to drain capacitance form what is known as the gate capacitance. And this is the capacitance seen at the input terminal of the MOSFET. It acts as the input load, capacitive load of the MOSFET, as well as the output load of preceding logic stages. The second class of capacitances arise from the PN junction that is formed between the source and the bulk, and the drain and the bulk. Okay, we know that the P region and N region here form a PN junction all the way around here, and at the interface of the P and N region there is a depletion region devoid of charges, and that separates the free carriers within the N region as well as in the bulk, and this gives rise to a capacitance. So these are collectively known as junction capacitances, or depletion capacitances from depletion region, or diffusion capacitances. This is an older term, and they are also called parasitic capacitances. Now let's take a closer look at the gate capacitances. The gate capacitance, gate to bulk capacitance, the gate to source capacitance, and the gate to drain capacitance is not a static value, and we'll try to explain why. If a negative voltage is applied to the gate, as you can, there is no channel here, the primary capacitance seen by the gate actually arises from the gate to bulk capacitance here. Okay, as an increasing positive voltage is applied, okay, when an increasing positive voltage is applied, there starts to be an accumulation of free carriers drawing closer and closer to the oxide layer, and this tends to reduce the capacitance levels seen between the gate and the bulk semiconductor, because you can think about this as the barrel plates of the capacitor are actually coming together closer, and this corresponds to this decrease here, this direction. And at V threshold, there is a sharp drop in the gate capacitance, because the formation of the channel here effectively disconnects or rather removes the capacitance between the gate and the bulk. But because there's this conductive layer connecting the source and the drain, now the gate to source and the gate to drain capacitances start becoming non-zero in value, because any fluctuation, any wiggle in the gate actually would affect would have an influence on the wiggle in the carriers in the channel and so on. So you see a gradual increase in the gate to source and the gate to drain capacitances, and the sum of both these capacitances form the gate to channel capacitance, and this gate to channel capacitance also tends to be equal to the initial CO. Now something interesting also begins to happen as we begin to apply a positive voltage across the drain to source. We know that that when the channel is formed, applying an increasingly positive voltage at the drain would result in a pinching off of the channel. And the reason this occurs is because the voltage difference at this region very close to the drain becomes less and gives rise to fewer carriers at this point here, and it pinches off the channel. And because there's presence of fewer carriers, we expect the capacitance value to go down. So the capacitance between the gate and the drain would start dropping as a function of VDS, but because of this pinch off behavior here, the bulk of the capacitance linking this body of charge here with this body of charge here will be shifted to the gate to source side. So the take home message from this is the capacitance seen at the gate of a MOSFET is a non-linear capacitance. It is not static. It is highly dependent on the operating regime of the transistor, namely the gate voltage and whether the transistor is in cutoff, linear or saturation regime. And in the saturation regime, we see a reduction of the total capacitance at the gate, whereas in the linear regime, we see a redistribution of the gate to bulk capacitance to the source and the drain terminals. One more factor to note in when you think about the composition of the gate capacitance in modern processors, typically the gate tends to overlap to a small extent with the drain and source regions, creating an additional overlap capacitance, and this overlap capacitance also contributes to the gate capacitance. As you can see here, it's parameterized by a normalized parameter, the overlap capacitance, and then multiplied by the width of the transistor. So transistors with twice the width will have twice the overlap capacitance. So all these together collectively form the gate capacitance. So the gate to source capacitance also comprises of a certain contribution from the overlap capacitance. Now let us talk about the parasitic, also known as junction capacitance, also known as diffusion capacitance, but in reality it actually arises from the depletion, the separation of charges caused by the depletion region between the drain and the source. This capacitance is given, please note that the depletion region, the region of depletion here comprises of the bottom plate right here, as well as the side perimeter of the end well here. And so the contribution to the junction capacitance from the bottom plate is this part here, a normalized coefficient here, multiplied by the width and the length of the end region, end dope region. So that's the area here, as well as the total area, that is the width and twice the length of the region, because we're going here, here, and here. Here multiplied by the some normalized parameter. So this is how we can calculate the contribution of the junction parameter, and all these normalized parameters are measured from the unique process which you use to fabricate your digital circuits, and they are included in simulation models of the digital circuits.